audience, my goodness. Whew. This conference so far has been incredible. Seriously, like, just the vibe here, the talks, the speakers. It's honestly such an honor to be invited to speak. So thank you all for taking the time to listen to my talk about offline and real-time apps, the magic of CRDTs. So, the next generation of tools is collaborative, right? Every single tool that we're using these days, we're expecting it to work in real time, to have that sense of like collaboration. We're spoiled, right? The tools we use these days are outstanding. Compared to 10 years ago, they are something else, right? If we look here, Office, email, Sketch, message boards, like they're kind of replaced. If anyone works on these projects, you know, I'm sure you'll get there one day. But Office is completely destroyed by things like G Suite, Google Docs. We expect that real-time collaborative nature. We expect to be able to, you know, hop onto a video call or just a voice call and talk about what we're working on in real time. Oh, you see where I'm clicking here? Let's add something over here, right? Especially as we all work remote, like this is the de facto. This is what we come to expect. But how do these tools work, right? It's a lot of algorithms and math and like all this kind of computer science witchcraft that for people like me who just move rectangles around, it seems super daunting. If you're curious to know how it works, we're going to be getting into it. Real-time sets this generation of products apart, and today we're going to start to learn about how we can go about building tools like these. So hi, I'm Matan Kushner. A bit about me. I'm the engineering lead at Tenkai. It is a Japanese comics publishing and distribution business. If you ever see these logos on the spine of a manga, on the spine of a book, Denpa for our mainstream stuff, Kuma for our LGBT content, and Faku for when you dim the lights and put on a scented candle. It's that kind of comic. Besides that, I'm also a developer on Annulist, which is a social cataloging site for anime and manga fans to talk about what they're reading and watching. And I'm also the lead maintainer of Starship, which is a cross-shell prompt written in Rust. But none of that has anything to do with real-time collaboration, right? Where do I have any experience? At Code Sandbox. So that was my previous gig where I was working on a real-time collaborative like IDE. They're doing incredible stuff, and the basis for a lot of the collaborative functionality was built by the team I was on. So we're going to dive into that. CRDTs, which is the technology that underpins a lot of how Code Sandbox and other collaborative tools works, is really the meat and potatoes here. So, as Yanni told us yesterday, CRDTs are conflict-free replicated data types. What that means is it's a kind of data structure. It's replicated, so every computer, every client, every phone has a copy of the state, has a copy of the data. And conflict-free means things don't go wrong when two people are changing the same thing. So how does that work? It looks a little bit like this. When you're in Google Docs, you're sharing the same document, but if you make changes in different spots, or even in the same area, it's going to at least resolve to something that is coherent, something that reflects the user's intent. It's not going to be just a jumbled mess of interleaved characters, right? We're going to end up with something coherent. So let's look at an example app. Here's a to-do list. This is my to-do list right now. I'm hoping to finish it up today. And we're going to be turning this otherwise single-player to-do list into a multiplayer one with CRDTs. So let's gradually go from one to the other. Here, this might be familiar to you. We've got an application state, so every to-do list item has a title and a status, whether or not it's completed. This should be familiar to you if you've used a reactive framework of any kind. As previous talks have been talking about state, here's some more state. So the other thing that CRDTs need, besides state, is what's known as an operation log. You can think of an operation log as like a list of steps needed to rebuild our state. So if we read from top to bottom, we can get back to our state. Step 1, at index 0, create a new array item with a given title and status. Index the second one and the third one, we're basically rebuilding the state if we're reading it from top to bottom in our operation log. So that means if we add something new to our operation log, a couple of state changes here, index 0, we're going to set completed to true, and index 1, our application state also is reflected. So that's the basis of how a CRDT works, is these two kind of bits of data. Now, the way that this goes on to be collaborative is that our operation log is what syncs between users. Our state stays on our machine, and the operation log, whenever something is added, gets propagated over to all our other users. And when they see these two things added, it's added to their own local operation logs, and from that we get an updated state. So as an example, we have someone else we're collaborating with, Liz, completes the third item, our operation log gets added to, and as a result, our application state gets updated. So that's the basis of how this works. That's how all the CRDT magic works under the hood. That's it. It's been a nice talk. No, we've got a little more. If only it were that easy. There's a whole lot that can go wrong in that process, right? Our mental model looks a little like this, right? Jade and Alex are pushing their data to the server. They're taking turns. It goes straight like that. Once it hits the server, it makes its way over to the other user. So our timeline is beautiful and clean, is what we would have liked. In reality, it's a little like this, right? We can't be assured the order is going to be consistent. We can't be assured it's going to be fast at all. If you're using your phone and you step into the subway and suddenly your half-completed tasks just linger, or you have super high latency because you're in Romania and you're messaging your friends in the States, they might end up a little out of sync. And this is further propagated when we've got servers doing the same things, right? If you're far from the server and the server is far from your friend, this whole round trip takes a long time. So we can't make the assumption that things will show up in order. Let's see how that might affect things with an example. We got Alex here, who creates a new to-do list item, do the laundry. And then Alex completes the task and does the laundry. Jade adds a new item, buy white bread. This is on their collaborative to-do list. The observant among you might see something's coming up, a bit of a problem. They're both occupying index 3 with their new to-do list item. So let's look at how this follows through. It both makes its way to the server, and then those tasks make their way to the respective users. Now, if we take a look, we'll see that Jade's task, index 3, is probably going to overwrite Alex's task at index 3, right? That's exactly what happened here. Alex now sees Jade's buy white bread in their to-do list, and Jade's sees do the laundry as completed, and neither of them have the tasks they wrote. We are completely diverged. They're both out of sync. This is the absolute worst situation you can be in, because then you have to start adding client and server code to reconcile and find out, what do we do here? Are we out of sync? You've got to be checking back and forth constantly whether or not all the users are seeing the same thing, even when they're all online, right? This is the worst thing that can happen. It's catastrophic. So how do we fix this? Well, we're going back to math class here, commutativity and associativity. If you're not a math whiz, you don't need to be. If I understood it, you absolutely will, okay? So commutativity, we'll start with that. If you remember this in math class, A times B is B times A, right? How does this apply to CRDTs, to our data structure? Well, Alex's state times Jade's operations should be the same as Jade's state times Alex's operations, right? If both of them have altogether all the same data, they should be seeing the same thing. On the flip side of that, associativity is basically the brackets shouldn't matter, right? No matter what order things happen in, they should be saying the same thing. These are the two of the three fundamental requirements of a CRDT. So looking back at our example, because Jade and Alex's operations came in different orders, they saw different things. That wouldn't work. That's not going to fly. We're going to have to change the way that this works. So looking back at our example, yeah, here are the two operations of Alex and Jade, and the order was super important. So what's the culprit here? Which bit of data here was causing issues? We kind of touched on it. It's the index. If we didn't have indices in this way, it wouldn't have been possible to run into this issue. So what do? Well, one solution is to replace our indices with IDs. If we use unique IDs per every to-do list item, it would be impossible to have that collision, right? They would be talking about completely different things. They wouldn't be overlapping each other at the same index. So that's the first principle of CRDTs. You need commutativity and associativity, and one way to enforce that is to have unique identifiers. So let's go back at our example here. We've got now the same situation. They're sending the tasks the exact same second, but the state they're both seeing has both to-do list items. They're talking about different to-do list items, right? That was their intent. Cool. All right. So just like that, we're commutative and associative. We can rest easy. Let's look at a new example, another situation where things might be able to go wrong. So we've got Alex this time who's offline, right? CRDTs aren't just for real-time apps, but also offline apps. In the case of like Google Docs, you can go offline, you can type some more things, you can go back online, and it needs to be able to resolve. So Alex offline, we've got shared state, which is cook a pot of pasta in their to-do lists. Alex cooks the pot of pasta, very responsible, and then he goes on to eat it. So it's incomplete again. He ticks it as done, and then unticks it as not done, because someone still needs to cook the pasta. And then he goes back online. Jade, in that time, cooks the pot of pasta. So we're going to run into a problem here. We're sending two differing completed states at the same exact moment. Ooh, how do we deal with that? As we were talking about last time, we got a box over here. We've got Schrodinger's cat for a completed state. Matthias was giving us a hint about what was going to go on here. And there's no real way to know what the completed state is without looking at it. And it's very possible that both users have different state. So let's actually make this associative, because it turns out we did a half job. We only kind of solved it. So looking back at our state, this time, what's the problem? Which piece of data was causing this issue? Last time it was index. This time it's not even here. There's no way to even see it, because it's actually time. Since both operations happened or were sent at the same time, we need a way to be able to resolve that. And the first step is to add a timestamp to our operations. Even if they were sent at the same time, they might have happened at completely different times, especially for offline users. So we're adding a timestamp here. This doesn't have to be like an actual millisecond Unix timestamp. It can be anything like a vector clock. We can get into that another time. But just think of it as time. Think of it as a promise of when something happened. And by adding that timestamp, we can then ignore anything that happened in the past in favor of anything that happened in the future, right? So we have to update our state a little bit. Instead of having just an array of to-dos, we'll have our list of to-dos, and we're also going to associate a time to every piece of state. So completed was last changed at that time, at the newest time. So if something comes in, and it's an old operation, it changes completed to false, but like in history, we're going to ignore it. Because, at least in our case, what matters is what's actually in the fridge. Was the pasta cooked, yes or no? So let's go back to our example, add some timestamps to our operations, and at this very moment, we know how to solve this. Jade's time is the latest one. So our time can be updated. The value is correct. We're good. We can rest easy. A+ for associativity. Almost. There's one last way that this can go wrong, and some of you might be seeing it. And that is our timestamp could collide, right? We could have two people making the same change at the exact same millisecond. What then? We need users' devices to be in sync. Well, what we could do, and this is kind of our final escape hatch, is we add an author ID. So every unique device or client is then given an identifier. This is also unique. So at the very least, it can tie break. So we look at which one has the higher author ID, and they are the ones that are right. It doesn't matter if what we're doing in the end is, is factually correct, right? Because both users are, like, one of the two users is going to be unhappy regardless. As long as we decide something, and then someone can go into their to-do list and be like, no, that's wrong, and they can fix it, right? We just need some consensus. So, finally, A++, we are fully associative. We're good. We're golden. All right, we've got commutativity and associativity. There's one third requirement for CRDTs, and that is idempotency. So, again, we're back in math land. This one's an easier one, right? A times A equals A. That's not always the case. I hope your math teachers taught you that. It is the case, though, in this example, and also in that one. So it's a rule. In our case, what that means is that if we apply the same operation multiple times, we should end up with the same state. This is excellent in situations where people might have a spotty connection, and they keep sending the same thing. Their devices, they might be trying to reconnect, packets might be lost, things might be lost in transit, and we need to make sure our application state isn't making a dozen items to feed the cats, right? We only want to feed them once today. Generally, they should be fed a lot. But yeah, it just turns out that idempotency, we already have it. Because of the timestamp solution and the author ID solution, we're actually good. We're golden. We have it by virtue of the way we implemented it before. So, just like that, we can see that we already have a to-do list item with that same ID. We don't have to make a new one with the same ID. We already have something at that timestamp. We don't have to make a new one at that timestamp. We're good. We're idempotent. Just like that, we've hit the 3 necessary properties of a CRDT. All right. What we've written is called a last write wins map. It is one of the fundamental CRDTs that is used in all sorts of products everywhere. It's also referred to as an LWW map for short, but there are CRDTs for all sorts of data types, for sets, for counters, for text, for strings, right? That's Google Docs. It's all just one big old string CRDT. But what we've got here is a map. And this is extensive, right? We only have one item here for completed. This could be extended to have all sorts of fancy properties, author, assignee, due date. If anyone here uses Linear, Linear, the task management tool, that's what they do. All their tool is a big CRDT. It's a last write wins map. Every property is just stored in this way, and they don't have like granular collaborative editing of like a single text field, like a description. But what they do have is just, if you're the last one to edit a property, it is what's saved. So CRDTs don't have to be like nitty-gritty deep into your app. You just something like this, and you're good to go. It's immediately collaborative. This is also extensible here to be kind of for a visual design tool. Figma, they also use CRDTs. It's kind of like this. Every property, layers, X, Y position, fill, stroke effects, they allow you to collaborate on modifying the same layer, and it's going to converge into something coherent. So you can have a user move a box, and you can have another user change its color, and you'll end up with the moved box with the changed color, right? That's why I'm showing off this CRDT, the last write wins map, because it's super common, and using just this, you already can have a collaborative tool. So, one last thing I want to show off is how can we make it so that we have sort order? Because when we had indices, we had an order to our to-do list items. Let's think about how we can implement that with our map. That was the animation that was supposed to play. So here we've got sorting. How do we implement that? We can add one more field, perhaps for order. The naive solution might be to add positions that kind of replaced indices, something like this. But then we end up with a bit of a problem, perhaps. What happens if you add a new value in the middle? Like, what should the position be? One option is to maybe make that then position 1, and then we have to cascade and make all the following ones have 2, 3, 4, and that's like a dozen operations we have to create from the one entry. The other easy solution might be to just make them floats, right? Give the position a half value of 0.5. This works perfectly well. This is how you turn your map into an ordered map, just like that. And like that, we've got sorting just working. So, CRDTs, one last thing I want to talk about is the server. What is the server doing here, right? The server, well, we send it some operations, and it sends it to the other users. That's all it's doing, though, right? It turns out we've figured out how to resolve our conflicts without any involvement from a server, from any authoritative entity. In the case that something does happen, because our algorithm is so elegant and handles things in a way that it's impossible to produce conflicts, the server doesn't need to be authoritative. So everything's super low latency because you just make state changes on your local client. You don't need to do round trips every time. You just do when you sync. So this server, truth be told, is kind of useless. It really is just a relay. It's just a proxy. It sends your requests to users and users' requests to you. And that is a lovely byproduct of CRDTs because our server does nothing. What that means is that this is also completely peer-to-peer compatible. You can have all these users on a same Bluetooth, Wi-Fi, network connection, whatever the case. Without a server, it can be fully encrypted. Like you don't. This is the kind of technology that can be working regardless of who's looking over your shoulder, right? It just works. That's the magic of CRDTs. It's so ridiculously elegant. So that really is it. That's CRDTs, the basis of it. They can be quite complex. I probably wouldn't recommend implementing this yourself unless you really know what you're doing, but we're lucky because there are many libraries that do it really well. YJS and AutoMerge are phenomenal JavaScript libraries. There are also services like Replicache and PartyKit and LiveBlocks that make this into beautiful React APIs to turn your otherwise local-first app into a collaborative app. So don't write this yourself. But now you know how it works under the hood. If you're ever inspecting your network traffic from these tools, or you need to debug something, this is it. So check out crdt.tech if this is interesting to you. Ink and Switch are the folks that did a lot of the leading research and state-of-the-art around CRDTs. So check them out if you want to see research papers on CRDTs. And that's it. Offline and real-time apps. Thank you so much for listening.